This semester we are going to see process control. Process control in instrumentation perspective. Instrumentation perspective. It is common subject for both chemical engineer as well as instrumentation engineer. Chemical engineer will see the process control in chemical aspect. Instrumentation engineer will see the process control in instrumentation control aspect. Today we are going to see the laboratory experiments. The first experiment is modeling, tuning, and closed loop control of level process. Modeling, tuning, and closed loop control of level process that we are going to see. Level process means it is nothing but like a overhead tank in a home. The overhead tank will be filled by a pump and it will be drained whenever water is in use. The inflow rate is Q in, so many liters per hour. Not inflow, inflow rate. Inflow rate means so many liters per hour. So many liters per hour. Similarly, outflow rate also, when it is in use, there will be so many liters per hour outflow rate. But that outflow rate Q out is equal to proportional to square root of that level. Square root of that level. Level in the tank. If you multiply by some constant, say B, then it is equal to square root of H. That's why it is a nonlinear process. What is a nonlinear process? This is H versus outflow rate, Q naught. If you plot, the relationship is a straight line. It is linear, but it is not so. The relationship will be like this. The relationship will be like this. That's why it is called nonlinear process. The relation between level and outflow rate is like this. If level is very less, the flow rate will be less. As level increases, flow rate will increase quickly. A nonlinear relationship. This is a nonlinear relation. This is linear relation. What you studied is linear control system. What you studied is a linear control system, not nonlinear control system. Here, we have to apply this linear control theory to control this level of this process. That subject is called process control. So most of the controllers that we are using is linear controller on a nonlinear system. A PID controller is a linear controller. We can linearize, we can find a linear model for this if the level is varying very small. That is called linearization of the process. If you linearize, then only you can find a transfer function. You studied so many transfer functions. In the control system, you studied transfer function, first order transfer function, second order, third order, like they are represented by first order differential equation, second order differential equation, third order differential equation, linear differential equation, no nonlinear relation there. That's why you can find the transfer function. If it is nonlinear function, you cannot find the transfer function. because you cannot obtain Laplace transform for a nonlinear function. That's why you cannot find the transfer function. If you find a Laplace transform, then only you can find transfer function. You cannot take Laplace transform means you cannot find the transfer function. So you cannot find transfer function. That's why we have to find an approximate transfer function, linear model that is called approximate transfer function. That process is called a linearization. If you obtain, then this model will be a first order process. If you obtain mathematical model of this level process, you will get first order model after linearization. Approximate model. Linearization means we are assuming that it is linear and we obtain the model, then it is called linearized model. That is theory that we will see later. If it is first order model, if you see the root locus, how many poles will be there? Only one pole. In closed loop, if you increase k, the root locus will move towards left. If you increase k, the root locus will move to the left. That's why it never crosses j omega axis. In S-plane, it never crosses j omega axis. That's why first order system is always stable. Stable first order system is, in closed loop also it is stable, always. Similarly, second order system. If you see the root locus of the second order system, of a stable second order system, it will be like this. If you increase k, how many, any point, if you select here, any point, if you select here, to its right odd number. That's why this is part of root locus. Then it break away and it goes like this. It never crosses j omega axis. But if you take a third order, break away, this goes to infinity and it will come towards this way. So we increase k, after some point it becomes unstable. Since it is first order, so you can use any value of gain k for a p controller. P controller means gain k, already I have told. The accelerator, if you increase, means you are increasing k. In a vehicle, to increase the speed, you are giving acceleration, means you are increasing k. For a first order system, any value of k is stable. No oscillations. If poles are on the j omega axis, you will get oscillations. But in practice, it is not first order. No first order, because in practice, what happens is, suppose I want to control this level process, means this is the level process. I want to control. Suppose I want to control the level of this tank, H means always I want to control this level. Suppose always I want to maintain the level of the tank 50% means you have to fill then and there, depends upon the outflow rate. The level is constant means outflow rate is B root H, that is also a constant. If level is constant means outflow rate also constant. Therefore, the inflow rate equal to outflow rate. Inflow rate equal to outflow rate. Am I correct or not? If inflow rate equal to outflow rate means level remains constant. How to control the level constant? For that, first thing is we have to measure the level. There will be a level transmitter that will measure the level. Suppose you want to control speed of a car means first thing what you will do, you measure the speed first. What is the actual speed we have to see? The actual speed is equal to the required speed, no need to control. If the difference is then we have to control. So first thing is we have to measure the level. Then only you will get the output. This is called a level transmitter. You studied level sensor. What is the difference between level sensor and level transmitter is transmitter means the sensor plus transmitter. Sensor plus transmitter is level transmitter. Level sensor plus transmitter is called level transmitter. All transmitters will give a standard output. It will give, if it is an analog transmitter, it will give 4 to 20 milliamps output. For zero level, it will give 4 milliamps. For full level, it will give 20 milliamps. Suppose I am having another tank. For that also, I am putting one level transmitter. But this tank is 10 feet height. This is 5 feet. If you put a level transmitter here, that also will give again 4 to 20 milliamps only. So the level transmitter is adjusted such a way that the tank is empty, it gives 4 milliamps. The tank is full, it gives 20 milliamps. For a chemical engineer, one tank is 5 feet, another tank is 10 feet. For instrumentation engineer, both are same. Because for both the tanks, the output is only 4 to 20 milliamps only. That is the difference between a chemical engineer and instrumentation. So instrumentation engineer has to look this as 10 feet at the time of implementing the level transmitter. Once it is implemented, he is going to see only 4 to 20 milliamps. The tank is 50% means 12 milliamps out. So I want to control this level of this tank. Always I want to maintain this level constant. Why I have to control the level? Why I have to control the level? In chemical industries means it may be a pharmaceutical industry, or it may be a fertilizer manufacturing industry, or some chemical manufacturing industry. In that, the 4 types of controllers, most of the controllers used for are the only 4 types: to control level, to control flow rate, to control temperature, to control pressure. These are the most commonly used controllers in chemical industries. pH control, some other controllers are there, but if we compare with these 4 parameters, that will be very less, very, very less. Why we have to control level means, suppose the outflow rate of this tank is given to another process. That process requires always 10 liters per hour. Always 10 liters per hour. The outflow rate Q out is given to next process, next unit. For that, it requires 10 liters per hour always. Means if you maintain the level constant, it will automatically get 10 liters per hour. I understand that. The tank is designed such a way that if you maintain the level of the tank 50%, the outflow rate will be 10 liters per hour. No need. So automatically the next process will get the constant flow rate. That's why we have to maintain the level constant. If you maintain the level constant, the next process, the next unit will get the constant flow rate. For that, we have to maintain the level constant. How to maintain this level constant? We have to adjust the inflow rate, Q in. Inflow rate has to be adjusted. To adjust the inflow rate, there will be a valve. A valve will be there. It is like a tap in your home. If you open the tap more, you will get more flow rate. If you close the tap, you will get less flow rate. Like that, this will open and close so that the flow rate will be varied. So you can adjust this flow rate equal to outflow rate. How to make inflow rate equal to outflow rate? We'll measure the level. If any change in level is there, then the controller will adjust this valve opening so that inflow rate will be adjusted. So the controller is looking for any change in level. If level decreases, it will open more, so more flow rate. If level increases, it will decrease the flow rate so that the level will be maintained constant. This is the valve used, pneumatic valve. The pneumatic valve used. The pneumatic valve means at home you will turn the valve clockwise, anti-clockwise to adjust the flow rate. Here we have to give pressure signal, 3 to 15 psi pressure signal to adjust the valve opening. Adjust the valve opening. For 3 to 15 psi, the valve will adjust the inflow rate so that the level will be maintained. So here the level transmitter gives the actual level. If you want, always you want to maintain 50% means the outflow rate will be 12 milliamps. That is available. That is available. Here, this is the signal, 4 to 20 milliamps. Actual level is measured and it is available as 4 to 20 milliamps. Why 4 to 20 milliamps? Why not 0 to 16 milliamps? Yes, what are you saying is correct. To understand the difference between live zero and dead zero, what he says is correct. If you put 0 milliamps means, suppose the transmitter is not working means, then also it will give 0 milliamps. For 0 level, it gives 0 milliamps. They are thinking the tank may be full, transmitter is not working. That's why it is giving 0 milliampere. But here, if you assume 4 to 20 milliamps means, if the tank is empty means it will give 4 milliamps, not 0 milliamps. The 4 milliamps is called live zero. The 4 milliamps is called live zero. Tank is empty, that's why it gives 4 milliamps. The transmitter is not working means it will give 0 milliamps. So we can understand that whether the transmitter is working or not. That's why it is fixed as 4 to 20 milliamps to differentiate the live zero and dead zero. So the live zero is 4 milliamps. That means tank is empty. 20 milliamps is tank is full. So it is given to the controller. Given to the controller. This level is called process variable. New term. Process variable. In control system, you studied it as a controlled variable or simply variable. Here it is called process variable because chemical engineers used to use process variable. The level is called the process variable. Suppose you want to control a pressure. The pressure is measured by a pressure transmitter that gives 420 milliamps. That 420 milliamps is called also, that 420 milliamps also called process variable. Process variable means variable to be controlled. Variable to be controlled, whether it is flow process or level process or temperature process or pressure process. So the process variable is in terms of 4 to 20 milliamps that is given to the controller. I want to control always tank 50%. That is called set point. Another new term. Set point. Set point is given as 50%. If the level also 50%, the process variable also 50% means no need to control. The difference between the two is the error signal. The error signal is given to PID controller. The PID controller output is depends upon the error. If error is more, control output will be more. That is also 4 to 20 milliamps. What is the difference between this 420 milliamps and this 420 milliamps? This represents the actual level. The actual level, when comes here, it is converted into 0 to 100%. Am I correct or not? 4 to 20 milliamps is converted into 0 to 100%. Set point also, you are saying 50%. That is also will be in the range 0 to 100%. So that the error will be in percentage. Error will be in percentage. So if the process variable is 52%, the set point is 50% means error is set point minus PV, that is minus 2%. Error is minus 2%, that is given as input to the PID controller. the PID controller, based on the 2%, it will give a controller output. That is again in terms of 4 to 20 milliamps. The error is 0 means 0 milliampere. The error is maximum means 20 milliampere. The PID controller output will be like that, 4 to 20 milliamps. But here you need 3 to 15 psi signal to control that valve. So this 4 to 20 milliamps has to be converted into I to P. That is, here you will give as input 4 to 20 milliamps is given to I to P. That will give 3 to 15 psi. Pressure signal. That pressure signal is connected here. Now it is in closed loop. Now it is in closed loop. Level is measured, given to PID controller. The PID controller gives output that is given to I2P. I2P output is given to the valve. Valve is adjusted so that level will be maintained. It is a closed loop control. Already we have seen that this is first order. But in practice, you cannot think it is a first order, because to know the level, you have to connect a level transmitter. That is, let us assume that that is also another first order. Another first order. No zero order in the world. Zero order means y equal to mx plus c equation you will get. Input is x, output is y equal to mx. No differential equation. Algebraic equation. No system in the world has is zero order. So minimum first order. That's why let us assume that the level transmitter is first order. So this level process and the level transmitter are cascaded, connected in series. You studied block diagram reduction. Two processes are connected in series means it becomes second order. Because level process is first order, another level transmitter is another first order. That's why it becomes second order. No more first order. But the level transmitter output is given to the PID controller. PID controller means it has the summing block is inside the PID controller. So in the PID controller, we will give this cross variable only. You can give set point manual by number. So these two will be compared. Based on that, it will give output. Let us assume that that is also another first order. It may be second order. Maybe second order PID controller. If you find the transfer function, it will be second order. But let us assume it is first order. We are using P only controller, let us assume. Another first order. No system in the world is zero order. So minimum first order. So now it becomes the order of the system becomes 3, because all the 3 are in series. In the loop. The loop means how you are drawing the closed loop system. Set point is given here. A PID controller is given here. The system is here. The output is connecting like this. This is the diagram that you are using in control system. But actually, you cannot connect like this, because the output here is 4 to 20 milliamps. That cannot be directly connected to the process. That's why one more I to P is there. That will be connected here. One more block. The output is in level. Level means in meters. You cannot give that to the PID controller. That's why you need a measuring device, level transmitter. That's the output is 420 milliamps. That is another block. So how many blocks are there? How many blocks are there? This is process one block. Transmitter is another block. Then a PID block. This is the PID block third. And then I to P. That is fourth block. So you cannot control by 4 to 20 milliamps. It should be converted into 3 to 15 psi pressure signal. So another first order comes into picture. Therefore, the minimum order of the system is 4. Again, this 3 to 15 psi cannot control the level. It has to adjust the valve. Valve is adjusting means that is another first order. Another first order. Let us assume. Therefore, 5 order devices are in series. Therefore, fifth order. Therefore, fifth order. So a level process, if you see, mathematically it is first order. If you see level process alone, but in practice you cannot control that alone. You need a level transmitter, you need a controller, you need I2P, you need a valve. If you connect all these things in series, then it becomes fifth order. So it is fifth order process. Fifth order process means you cannot increase gain beyond a certain value. From third order onwards, if you increase K, what will happen? The poles will move towards right hand side. At one point, it becomes K max. That at that point, it exhibits sustained oscillation. If you further increase, it becomes unstable. It becomes unstable. That's why the bike is minimum third order. Bike, let us assume that it is first order, maybe higher order. You are looking at the speedometer you connected in series with that. That is another first order. So minimum second order. You are looking the speedometer through your eyes, third order. The output of the eyes is given to the brain, fourth order. The output of the brain is given to your hand, fifth order. That's why if you go increase gain beyond a certain value, it may become unstable. That's why oscillation comes. Suddenly anything happens, you cannot take decision. The oscillation, we are very close to J omega axis. That's why oscillation comes into picture. So here, this is minimum fifth order. That's why you cannot increase the gain of this PID controller beyond a certain value. So we have to fix the value so that one reason is the system must be stable. What is the expression for PID controller? The output of the PID controller is M of T. M of T is a function of error. Already I told you that if error is more, controller output will be more. Therefore, I can say that the controller output M of T, that is 420 milliamps, M of T is a function of error. Because input to the controller is error, it is function of error. What is the expression for if it is a P controller? Kc multiplied by error. If it is Pi controller, integral mode means 1 by Ti integral of E dt. Suppose let us assume that we are using Pi controller, not PID controller. Let us ignore the derivative mode. Only P mode and I mode if you use, this is the expression for PID controller. Here Kc is there, Ti is there. Kc is for entire function, that is gain of the controller. If you increase gain of PID controller, that is nothing but gain of the process you are increasing, gain of the system you are increasing. So if you increase Kc beyond a certain value, the process becomes unstable. That's why we have to fix the value of Kc. At the same time, if you give a very small value, it takes a long time to adjust to the level. That is also not acceptable. Suppose I am asking you to solve a sum, sir, it will take 1 hour to solve. 5 minutes sum, if it take 1 hour to solve, is it acceptable? It should done quickly. At the same time, if you increase Kc beyond a certain value, it becomes unstable. That's why you cannot increase beyond a certain value. At the same time, it has to do in a reasonable time. That's why we have to find the compromise between the two. The limit is there for Kc. Kc max is there. That's why how much Kc we have to select for acceptable operation, not best operation, acceptable operation. For that, what is the value of Kc we have to find. Similarly, for Ti, if Ti equal to 0, it becomes infinity. Ti also important, even though it is in the denominator, that also plays a role. 1 by Ti means Ti becomes 0 means infinity. So that also we have to fix. So the fixing the value of Kc and Ti is called tuning of controller. Tuning of controller. What is the title? Closed loop control. Already we have seen that if you want to control something, you need a closed loop. We have to measure the level, compare with the desired value. Based on the error, we have to adjust the input. It is closed loop control. In that, a PID controller, if you put a PID controller, there are two parameters, Kc and Ti, that has to be adjusted. Can I use the same Kc, same Ti for all process? No. Suppose two level process are there, both are 5 feet. Can I use the same? No. Because for that, we have seen already one example. I am using a old car now. For that, I want to adjust the speed means I know how to give acceleration to adjust the speed. Suppose tomorrow I'll get a new car means I cannot apply the same algorithm to adjust the acceleration there. It will be very fast. That's why the characteristics of the system is important to fix Kc and Ti. That's why for each and every process, we have to find separate Kc and Ti. It varies from process to process. Based upon the process, we have to find Kc and Ti. Finding Kc and Ti is called tuning of controller. For this process, what could be the value of Kc and Ti? That is called tuning of controller. So we have to do tuning. Then only we can do closed loop control. Next thing is modeling. To fix the value of Kc and Ti, we need the characteristics of that system. If you obtain the mathematical model from the first principle, you will get first order model. You cannot work with that because if you know the mathematical model of level transmitter, mathematical model of PID, mathematical model of I to P, mathematical model of control valve, if you combine all these together, you will get the mathematical model of this system, this unit. If you know the mathematical model of level process alone, you cannot apply here. That's why we have to find the mathematical model of this system, entire components together, so that we can find the tuning parameters. Two ways are there. If you know the mathematical model of each component, each level transmitter, PID, ITP, and valve, if you combine all these together, you will get fifth order transfer function that can be used to tune the PID controller. That you do not know. You do not know the mathematical model of valve. You do not know the mathematical model of I2P. You do not know the mathematical model of PID controller. You do not know the mathematical model level transmitter. That's why it's difficult, tedious. If you know, you can find it. The another way is finding experimentally how to find the mathematical model. For that, we have to understand the response. Suppose I am finding the step response of first order process, it will be like this. This is a first step response of a first order process. I am having step response of a second order process. Both are settled at say 5. This is also settled at 5. What is the difference between the two? Time is different. Yes. So time constant is different. Not only that, if you see the initial slope here 90 degree. First order. Here initial slope is not 90 degree. If it is a first order system, initial slope will be 90 degree. Theoretically, initial slope will be 90 degree. But it is not so in the case of second order. As order increases, suppose I am having a fifth order means it will be like this. As order further increases, 10th order means it will be like this. Further delay. This is 10th order. This is 5th order. This is called transportation lag. There is a lag. You can notice this. Let us assume that all vehicles, all cars are first order. Let us assume all are standing in the signal. You are standing as a 5th car. Signal is changed. All cars are moving together. It takes some time because of that delay. Each process, some delay is there because each one is of first order. If it is algebraic model, 0 order means as soon as signal is changed, all car will move together. That can be done only in mathematics. Practice, it is not possible. So you have to wait. If it is 10th car means you have to wait more. First 10 seconds, there won't be any movement for the 10th car. So if we cascade many first order systems, there will be a delay in the output. So this is 5th order. So I can model this as like this. I can model this as like this. So I modeled like this. I am ignoring the small increase. I can model like this. Can I model like this? These two are identical. These two are identical. Can I model like this? Just I am approximating the process like this. The 4th order is modeled like this. This is the 5th order process. This is 1st order. I am approximating this 5th order with 1st order. What is the difference between this 1st order and this? In this 1st order, there is no delay. In this 1st order, there is a delay. So I can include this delay as TD, dead time. So I can model this 5th order as 1st order with the dead time. I can model this as 1st order plus dead time. What is the model of this 1st order? Time taken to reach 63.2% of final value is called time constant. You know the definition for time. So 10 feet height means time taken to reach 6.23 feet. What is the time? That is time constant. So the model of the process is G of S equal to 1 by time taken to reach 6 feet, 6.23 feet is the time constant, Ts plus 1. This is the model of the process. Gain you can put in the numerator. So you can obtain experimentally like this. Mathematical model can be obtained. 1st order mathematical model can be obtained like this. So what is the time taken to reach 63.2% of final value? That is the definition for time constant. By using that, you can find, this is this is experimentally finding the mathematical model. Time taken to reach 63.2% of final value. Like that, if I find time taken to reach 63.2% of final value means I'll get the time constant so that I can approximate this as 1st order process. So 5th order is modeled like 1st order. So what is the time taken to reach 63.2% from this point? From this point, not from the initial point. Where it starts rising, this point. From this point, what is the time taken to reach 63.2% of final value? So that I'll get time constant. So I got the mathematical model, 1st order model. What is the drawback here? Initially, some delay is there. That is called dead time. So if I include that dead time, e power minus TDS. So that much a delay is there. After that, it behaves like 1st order, if we tell. So experimentally, I can find the mathematical model of 1st order. Only thing is, I am approximating this response like this. No output for TD time, TD seconds. So the 5th order is modeled as 1st order plus dead time. 1st order plus dead time. 1st order plus dead time. So any higher order process can be modeled as first order plus dead time, because the delay is given as dead time. Up to so many seconds, there is no output, we are assuming. After that, it behaves like first order. So experimental method. So if you obtain this mathematical model, you can find Kc and Ta. Ziegler-Nichols says, if you know K, T, K, tau, K is gain, tau is time constant, Td is dead time. If you know these three components, you can find Kc, Ti. He tell the thumb rule in 1949. 1949, he said the thumb rule to find the tuning parameters. Those time no electricity. That time they found. Instead of electrical signal, pneumatic signals are used. Instead of 4 to 20 milliamps, 3 to 15 psi is used. The level transmitter will give 3 to 15 psi. PID controller output will be 3 to 15 psi. Input to the PID controller is 3 to 15 psi. Everything is working in pneumatic signal. That time he found a formula, but we have so many sophistication, but we won't find anything. So that time they found the formula that if you know K, that is gain of the system. Gain means what? Ratio between change in output by change in input. Gain. If you know the time constant of the process, time constant means what? Time taken to reach 63.3% of 32% of final value. 63.2% of, sorry, 63.2% of final value. That time is called time constant. If you know time constant, you know the dead time. If you know these three, you can find the tuning parameters. He said, by using that formula, you can find Kc and Ti. 0.9 times T upon K Td. Ti equal to 3.33 times Td. The dead time multiplied by 3.33 times Td. If you know this formula, thumb rule, not formula, by using this thumb rule, you can find Kc and Ta. So to find the appropriate value of Kc and Ta, we need the mathematical model. Theoretically, it's not possible, feasible to find the mathematical model. That's why we are finding experimentally mathematical model. We are finding experimentally mathematical model. How to obtain that? How to obtain mathematical model experimentally? For that, what we have to do is, we have to bring this process to 50% first, because always you want to control 50%. Always you want to control 50%. The level is at 50%, outflow rate is different. The level is 70%, outflow rate is different. What is the formula? B root h. Outflow rate is B root h, that is nonlinear relationship. That's why we have to bring the level first to 50% to obtain the mathematical model. Because if you obtain mathematical model at 25%, it will be different from mathematical model at 50%, the mathematical model at 75%, the mathematical model at 90%. It will be different because it is a nonlinear process. For small changes only, we are going to find the mathematical model. For large changes, it may not work. Those things are all we will study in theory. So first thing is, we have to bring the process to 50% level. This controller is useless control. This controller is useless controller. What is the expression for the controller? M of t equal to Kc multiplied by E plus 1 by Ta integral of E dt. It is function of E only. Already we brought the process to 50% by some other means. Let us assume by some other means I brought the process to 50% level. What is the error? What is the error? Set point is 50%, level also 50%. What is the error? 0. Control output is 0. The valve opening is 0. No input. I understand this point. So this controller is useless. This controller is useless because it is function of error only. That's why we cannot use that. We have to make it practical. We have to make it practical. It is not practical PID control. It is theoretical PID control. What you studied in control system is theoretical PID control. So practical PID controller, we have to add one more term that is called the bias. That is called bias. Bias, you know. அந்த வாரியார் பயஸ் பண்றாரு சார், அந்த பையனுக்கு கூட மார்க் போடுறாரு, எனக்கு குறைச்சி மார்க், இந்த பையனுக்கு 10 மார்க் பயஸ் சொல்றோமா இல்லையா? Bias means additional. Bias means additional. So this bias is required. Then only there will be a flow rate. When the controller, when the error is 0, there must be a controller out. Then only you can maintain it 50%. Then only you can maintain it 50%. To maintain 50%, bias is required. Because the controller output is 0. You've seen that the controller output for set point equal to 50%. What is set point? Reference. I want to maintain at 50% means set point is 50%. What is the process variable? That is also 50%. What is the difference between the two? 0. Therefore, controller output is 0. Therefore, valve will not open. But the valve has to open to maintain that 50%. To maintain that 50%. For that, let us assume that valve is open to 50% always. Always valve is open to how much? 50%. The bias is 50%. Bias is 50%. That's why valve is always open 50%. Therefore, level is always 50%. That's why there is no need of PID control. Useless control. Bias alone is sufficient. If it works perfectly, bias alone is sufficient. You understand this point? I am giving 50% bias. Valve is 50% opened. Valve is 50% open, therefore 50% flow rate, therefore level is 50%, set point is 50%, error is 0, therefore no need of PID controller. Am I correct or not? This is theoretically good. Practically it may not work. Practically it may not work out. Valve is open to 50% means it may settle at 55% or 45%. Valve is opened how much? 50%. 50% means what is the current signal? 12 milliamps. What is the pneumatic signal? 9 psi. Middle value is 9 psi or 12 milliamps. If we give, the valve will be open to 50%. The valve is open to 50% means level must be 50%, theoretically speaking. Because we only designed the valve, we only designed the tank, we only designed the outflow rate. That's why theoretically we designed such a way that if valve is open to 50%, the level will be 50%. But it is not so in practice because of that non-linearity and so many other things which is ignored while designing. That's why it may not be at a 50% level. Let us assume that for 50% valve opening, the level is 50%, set point also 50%. Then whether we need valve, controller, yes or no? No need. Suppose I want to change now I want to change the level to 55%. Now it is in 50%. I want to change it to 55%. How to adjust? If it is closed loop controller, what I can do is simply I have to change this to 55. That's all. The controller will take care and it will bring to 55. That's why you need the controller. That's why you need the controller. If you change the set point, you need the controller. If you change the set point, you need the controller. Not only that. Another reason you need the controller. Another reason is disturbance. Car is moving at 60 kilometers per hour. Your set point is 60 kilometers per hour. Can you expect always 60 kilometers? Cannot, because the slope of the road may change. The wind direction may change. That's why speed may change. Therefore, you need a controller. You have to adjust the accelerator so that speed will be maintained to 60. In the same way, here also disturbance may come. The valve is opened 50%. Here, the liquid is coming from some other tank. Some other tank, let us assume. It is coming from some other tank. In the tank, earlier it is full. Now it is 78%. Is there any change in flow rate for the 50% opening? Definitely. At your home, you can experience that If you open, tank is full means if you open less, there will be more flow rate. Tank is very low means if you open the same amount, there less flow rate. So even though the valve is opened 50%, because of this disturbance in some other place, it will affect the inflow rate. That's why you cannot expect for the same opening, always same flow rate, you cannot expect. That is called disturbance entering into the system. Here, disturbance is different. In a car example, the wind and the slope only are the disturbances. Here, so many disturbances are there. One example is the upstream pressure. This is called another new term. This is called upstream pressure. Upstream pressure may change. Because of that, the flow rate may change. If it is open to atmosphere means downstream pressure. If upstream pressure changes, flow rate changes for the same valve opening. 50% is opened, but flow rate is decreased because upstream pressure decreases. Downstream pressure means pressure at this point. That is also required for some another experiment. That's why I'm telling now itself. So here, downstream pressure is open to atmosphere. This tank is open to atmosphere. Therefore, downstream pressure is constant. If this tank is closed one, downstream pressure also will change. Inside air is there. If the level increases, pressure will increase, Therefore, downstream pressure also will change here. If it is a closed tank. So, there are so many disturbances, depends upon the design. So, those disturbances will be managed by controller. Those disturbances will be managed by the controller. I understand that. Suppose the density of this liquid, don't think it as a water. Let us assume that it is a liquid, some chemical. Its density may change from today, tomorrow, day after tomorrow. Its density may change. Depends upon the density, outflow rate will change. Depends upon the density, outflow rate will change. Small change, but after a long time, there will be a large change in level. You understand this? Let us assume that density is decreased. That's why outflow rate is increased. Outflow rate is increased. Small amount increased. But after 5 hours, level will be drastically reduced. So you need a controller. Why controller is required? To change the set point. To change the set point. One reason. Another reason is to take care of disturbances. To take care of disturbance may enter many ways. It may be because of upstream pressure, or it may be because of downstream pressure, or it may be because of change in density of the liquid. Many reasons are there. Because of that, the level may change. That also will be taken care by this controller. That also taken care by this controller. No need to know why level is decreasing. It won't ask. If level decreases, it will open the valve more. Yesterday, I opened 50%, this much flow rate. So for this error, I will open this much only. It won't say. If level decreases, automatically it will open more. That is function of PID controller. So if any disturbance entering into the process, there will be a change in valve opening. That is done by this controller. This way it will be controlled. How to find the bias? I said you need additional flow rate is required to maintain 50%. How to find that bias? How to find that bias? For that, what you have to do is, you have to open some 10%. You want to maintain 50% means, you should not open 50% immediately. If you open 50% means, it may either settle at 40% or 60%. Then you have to adjust 60 to 50 or 40 to 50. That's why they will open gradually 5%. Once it is settled, then another 5%. Gradually, they will increase. As soon as it reaches 50%, they will adjust very small amount. Once it reaches at 50%, what is the controller output? They will check. That output is called the bias. That's why there are 2 modes in the controller. Viewpoint. There are 2 modes in the controller. One is called automatic mode. Another one is manual mode. In manual mode, you can adjust bias. In automatic mode, the controller output will be based on error. Automatically, the controller will calculate what should be the controller output, and it will add it to the bias and it will give out. So bias always will be there. Whether it is in manual mode or auto mode, bias will be there. Bias will be there. That's why in manual mode, you can adjust bias only. In auto mode, you cannot adjust even bias. So in manual mode, suppose the controller, this is the controller, PID controller. I am putting this in manual mode. There will be increase, decrease button like this, increase, decrease button. This is the controller output 4 to 20 milliamps. If you press in manual mode, this, the controller output will increase from 4 to 20 milliamps. It will increase. If you press this, it will decrease. That's all in manual mode. If you put this in auto mode, you cannot adjust the output. Cannot adjust the output. That will be based on this formula only. What is the formula? Kc multiplied by error plus 1 by Ti integral of EDT plus bias. What is bias? Bias is whatever the output you gave in manual mode. Bias is what? Whatever the output you gave in manual mode. Once you transfer from manual mode to auto mode, the auto mode output will be this formula plus bias. Suppose in bias manual mode, I am adjusting the controller output to 12 milliamps. The level is settled at 50%. Level is settled at 50%. Now I transferred from manual mode to auto mode. What is the controller output? I am repeating the statements. I am putting the controller in manual mode. I can adjust, already I told in manual mode I can adjust. I am adjusting the controller output to 50%. What is the controller output? 12 milliamps. Because total controller output is 4 to 20 milliamps. You adjusted to 12 milliamps. Therefore, how much value is opened? 50%. Because you are giving 12 milliamps. What is the level? 50%. What is the level? 50%. You understand this? Now I transfer to auto mode. What is the controller out? M of t equal to Kc multiplied by anybody else? Uh, 1 by Ti E dt plus bias. The bias can be adjusted only in manual mode. Once again, I'm telling, third time I'm telling the same statement. Initially I put the controller in manual mode. I am adjusting the bias. I made bias equal to 50%. Bias equal to 50%. In engineering units, it is 12 milliamps. Am I correct or not? I cannot touch this in manual mode. You can't do anything. What is set point? 50%. What is PV? 50%. Set point means reference. Cross variable means output. Actual output. Actual output. I want to ride the car at 60 kilometers per hour. I want to ride the car at 60 kilometers per hour. Therefore, 60 kilometers per hour is called set point. The car is now moving at 58 kilometers per hour. What is PV? 58. I understand this. Remember this. So I made bias equal to 50%. That is 12 milliamps. Valve how much opened? 50% open. The tank is filled to 50%. Am I correct or not? Because 50% valve open. The level is filled to 50%. Set point is 50%. Now what is the output of the controller in auto mode? I changed it to manual mode to auto mode now. I changed it from manual mode to auto mode. Manually, I gave 50%. What is the auto mode output? Now use this. Huh? Yes. Who said? Correct. Okay, anyhow. Set point is 50%, PV is 50%, therefore error equal to 0. Am I correct or not? Error 0 means that this entire output is 0. Bias only will come out. In auto mode also, bias only will come out. Therefore, 50% again. That's why the same 50% will be maintained forever. There is no disturbance. There is no change in set point. If I come tomorrow, the same 50% will be maintained. I understand this. In auto mode also, the controller output is same 50% because the error is 0. Suppose some disturbance is entered, that's why level is reduced to 48%. Therefore, error becomes 2%. Therefore, you substitute the 2% here. Here also you substitute the 2%. Now, controller output is increased beyond 50%. You understand that? Suppose because of disturbance, the level is changed to 52%. What is the error? Error equal to minus 2%. That's why there will be a decrease in error. Error is in negative. That's why decrease from 50 to 48%. Let us assume that. I understand this point. I understand. We do not know what is the quantity. We do not know. Some changes happened because we do not know the value of Kc and the Ti. We do not know the value of Kc and Ti. Some changes will happen because of error. If error is there, then only the PID controller will work. That's why that is theoretical control. In practical controller, you need a bias. Without bias, you cannot use the PID controller. That's why we have to throw it away. Theoretical controller we cannot use in practice. To use in practice, bias has to be added. Bias has to be added. So how that? And now I will tell how the controller works. How I will tell. Initially, you want to control the level at 50%. For that, what you have to do is you put the controller first in manual mode. First, you have to put the controller in manual mode. Manually, you adjust the controller. Let us assume that by luckily, if I give 50% controller output, level also 50%. That's why I can stop at 50%. Controller output is 50%, valve opening is 50%, level is 50%, set point is 50%. Therefore, error is 0. So, if I transfer from manual mode to auto mode, it remains at 50% unless otherwise any changes happens. Do you understand that? I understand this point. If changes happens, the controller will take necessary action to change, do the necessary corrections. That transfer is called. This transfer from manual mode to auto mode is called bumpless transfer. Another new word. Bumpless transfer. The pilot, if you want to travel from India to United States, New Delhi to United States, or Bangalore to United States, if we take off here, it will land in United States only. Some 25 hours, approximately, I do not know. I never went to United States. So 25 hours running. Pilot won't monitor the speed. You'll put the set point, say 900 kilometers per hour speed. He'll fix. And altitude also fixed. Altitude also fixed. From ground to altitude is fixed. If any change is there, automatically the controller will take. I am not talking about, I am talking only about one variable. Speed. Speed is fixed as 900 kilometers per hour. This you cannot put at the ground. You cannot put the controller in action at ground level. Once it reaches 900 kilometers per hour and the correct direction, then you can put in autopilot mode. You can put it in autopilot mode so that the controller will adjust if any changes there. Any density, air density changes, speed will change. Air density changes, speed will change. Altitude changes, speed will change. So, if any speed is changed, the controller will take necessary action. Bias value, pilot has to find. Bias value, pilot has to find. For another reason, how you will reach 80 kilometers per hour in car? Initially, you put 5th gear and you go to 80 kilometers per hour. First, you will put the first gear up to 10 to 15 kilometers per hour. Once it reaches, you put second gear. After 10 kilometers, you put second gear. Then once it reaches 20-25, you put third gear, fourth gear, then 5th gear. Nowadays, 6th gear also there. 6th gear. You can put like that. So, there is a non-linear relation between this speed and acceleration. That's why you cannot directly put the PID controller in action like that. To understand, I'm telling this example. So you have to bring to the speed 900 kilometers per hour. Then you put it in the PID controller, means it will take care. For 900 kilometers, 50% is PL is pumping. That's why it is moving at 900 kilometers per hour. Any change is that it will adjust about 50%. So the function of PID controller is not opening 50%. It will adjust about 50%. You understand the difference? It will adjust about 50%. That only it can do. If any change is there, for that only it can control. Because of one reason is because of non-linearity. Because of, I cannot talk about that. It is a very big topic. We'll see later. Because of that non-linearity, you cannot find the linear relation for that bias. So bring initially to that final value, make set point equal to PV, error is 0. That time if you transfer from manual mode to auto mode, the output at manual mode and auto mode are equal. Am I correct or not? Because error is 0. That type of transfer from manual mode to auto mode is called bumpless transfer. Bumpless transfer. Why bumpless transfer is that required? Bumpless transfer means how you will get into a running bus. How you get into a running bus? You will run along with the bus first. You will bring your speed equal to bus speed. Then you will jump into that bus. Am I correct or not? So initially we have to run along with the bus. Then if the speed is equal, then we will get into that bus. That is, it is like that. Bumpless transfer means seamlessly you have to transfer from manual mode to auto mode. Suppose I left in auto mode, some disturbance is coming. Auto mode, I left in manual mode, some disturbance is coming. Manual mode I fixed at 50%. There is no formula in manual mode. There is no formula in the manual mode. That's why if disturbance comes, level will be changed. Level will be changed. But if you put it in auto mode, that formula now 0 because error is 0. But if any error comes into picture, this formula will work out and find the additional output automatically. You understand this point? So transfer from manual mode to auto mode seamlessly. For that, set point must be equal to PV. Set point must be equal to PV. For that, 3 conditions has to be satisfied. So if you transfer from manual mode to auto mode, that is called bumpless transfer. To do bumpless transfer, 3 conditions has to be met. One is it remains at 50%. It remains at 50% because set point equal to 50%, cross variable also 50% means it remains at 50%, means it should be at steady state. It should be at a steady state. Steady state value means what? Already you studied what is steady state. You are it increases like this and finally it remains at 50%. This part is called steady state value. So it must be at steady state. You have to make set point equal to PV. Set point equal to PV equal to 50% because you want to maintain at 50%. Second condition is make set point PV. Third point is there must appropriate value of Kc and Ta must be there. Suppose Kc you gave for unstable value, very large value of Kc you gave means any disturbance comes, the process becomes unstable. It should control the disturbance. It should reject the disturbance. For that, appropriate value of Kc and Ta must be given. So if 3 conditions are satisfied, if you transfer from manual mode to auto mode, then it is called bumpless transfer. The process should be at steady state. Suppose, let us assume that you gave some opening, 50% opening. The process will settle at 60%. Definitely it will cross 50%, That time you transfer from manual mode to auto mode. That will not work out. Because for the bias value itself, it will settle at what? Where? 60%. Now you transferred from manual mode to auto mode. Now the output will go on increases because the bias itself will settle the process at 60%. That's why the controller has to take necessary action to bring back to 50. It takes long time. It takes a long time because 10% change is very large, very, very large as far as controller is concerned. Because if any small change, it immediately will correct. For 10% change, it takes 2 to 3 hours to correct. That's why set point must be equal to PV at steady state, not a transient. Suppose you gave the bias value so that the cross variable will settle at 60 means when it comes 50, definitely it will settle at 60. When it crosses 50, you are thinking that it is set point equal to PV, so I can transfer from manual mode to auto mode. It will not work out. So this set point must be equal to PV. The set point must be equal to PV at steady state. That is first condition. Second condition is set point equal to PV. Third condition is we should enter the appropriate tuning parameters. Appropriate tuning parameters. How to tune that? By using that thumb rule, by using Ziegler-Nichols formula, by knowing K and T and TD, dead time, time constant, and K, we can find the tuning parameters. How to find the tuning parameters that we'll see now. How to find the tuning parameters that we'll see now. So what and all so far we have seen. So how to tune the PID controller? First thing is you have to obtain the model. To obtain the model, two methods are there. One is theoretical. By first principle, you can obtain. That will not give the fifth order model because other things are there along with the level process. Experimentally, we have to find. Experimentally, we can find it as a first order plus dead time model. That is, the fifth order will be looking like this. Up to this will be taken as dead time. This reaction curve will be, this part will be modeled as first order. How to obtain this? Time taken to reach 63%, 63.2% of final value. What is that value? You have to find that is time constant, Ts plus 1. K is the relation between input output. You opened 2% increase in input. Change in level also 2% means gain is 1. You opened input 2%, level is changed to 4% means 4 by 2 equal to 2, K equal to 2. That is K. This delay is, the delay in the response is called a dead time. That is E power TD. Yes. If you know this, you can find the tuning formula. How to obtain this reaction curve. Another new term. This is called a reaction curve. Reaction curve. How to obtain this reaction? To obtain reaction curve, first you bring the process to 50% level because you always want to operate the level at 50%. So bring the process to 50% first manually. Put the controller in manual mode, manually adjust the controller output. In manual mode only, you can adjust increase, decrease. I already told you that there is one button. This is increase button. This is decrease button. By using this increase button, you can increase the output or you can decrease the output by using this. This 420 milliamps will be changed in manual mode. By adjusting that, you can bring the process first to 50% level because nominal another new term. Nominal operating point is 50%. Nominal operating point means always I used to maintain at 50%, meaning today I may maintain at 52, today I may maintain at 48, today I may maintain at 54, but at an average I used to maintain at 50%. That is called nominal operating point. So bring the process to nominal operating point by adjusting manually. So now the process is settled at nominal operating point, say 50%. When it is settled at 50%, when reaches steady state, you increase the controller output by 5%. Let us say that you opened the controller 50%, the valve is opened for 50%, level is settled at 50%, steady state is 50%. That time you increase the controller output to 55%. How much you increased? 5%. So increase in controller output is 5%. Now start noting the controller output, change in level. You increase from 50 to 55. It is settled at 50 now, steady state at 50. That time you increase the input to 55, it starts increasing level. Note down, every 3 seconds you note down. You plot like this, time versus level. That is called reaction curve. The reaction curve will be looking like this because it is a fifth order system. That's why it will be looking like this. Reaction curve you will get. It is settled at 60. Now, initially it is at 50. Now it is settled at 60. Change how much? 10%. Therefore, K equal to Kp. Process gain. Kp equal to change in output. Change in output by change in input. What is the change in input? 5%. What is the change in output? 10%. 10% by 5%. Therefore, change in gain is 2% per person. 2% per person. That is K. In this model, you got K. What is the model I said? What is the model I said? K upon tau s plus 1. K you got. Initially it is 50%. You change 5%. You settle at 60. Therefore, K equal to 10. Time constant, how to find? Truncate up to this part. Truncate up to this part. Now, here it is settled at 60. From 50 to 60. What is 63.2%? That is 56.3%. 56.3%. What is the time taken to reach 56.3%? 32%. 56.32%. What is the time taken? This is TP, time constant. From this point, that is TP. So find TP, that you got. Already you got Kp, TP you got. Measure this time. There is no output for some time. Measure this time. That is TD. That is TD. This is TD, TP, Kp. How to find? Change in output by change in input. Therefore, you got the mathematical model TDS. If you know these three, you can find the tuning parameters. The tuning parameters can be found by using this formula. This is the formula. Already I told Kc equal to Tp divided by T by Kp, I said, or Tp, process time constant. Tp by Kp multiplied by Td. If it is a P controller, if it is PI controller, 0.9 times Tp by Kp Td. Ti equal to what? Ti equal to 3.33 times Td, dead time. If it is a PID controller, this is the formula. We are not going to use PID controller. Either P controller or PI controller will be used for level process. That's why first two formula only will be used. This is called Ziegler-Nichols thumb rule. Ziegler-Nichols thumb rule. Ziegler and Nichols both found this formula. Still it is used. In 1949, no one accepted that. Ziegler-Nichols formula. By using that, we can find the tuning parameter. So once you got tuning parameters, again made to 50. Because I want to control where? At 50%. Again, I made it to 50. Again, it is settled at 50. I entered the tuning parameters in the controller, Kc value and the Ti values. The process is at steady state at 50%. Set point is 50%. Now I can transfer from manual mode to auto mode and leave it. The controller, even if it takes 1 year, the controller will control at 50%. Whatever the disturbance comes into picture, the controller will take care of it. The controller will take care of it. So this is called modeling, tuning, and closed loop control. Once you did the complex transfer, it remains at 50%. Why? Set point is 50. Cross variable also 50. That's why it remains at 50%. There is no analytical controller out because error equal to 0. So now we have to do the experiment. After doing all these things, we have to do the experiment. One is called servo response. Another one is called regulatory response. Servo response means you have to change the set point. If you change the set point to 50 to 55, already it is at 50%. You change the set point to 55%. Now, the controller will change like this, the level, and oscillate. Finally, it will settle at 55. You can dictate to the controller. I want to change it to 55 means controller will take care. It will change to 55. Suppose you ask the controller again. Now it is settled at 55. Now again change the set point to 50. Suppose you want to change set point, 50 means it will come like this and oscillate and finally settle at 50. So you can do this type of response is called servo response. Servo response. Servo response means servo start with S. Servo response means change in set point. Servo response means change in set point. If you do that deliberately, if you change the set point, then it is called a servo response. Another response is called a regulatory response. Another response is called a regulatory response. It is at 50%. You are not changing the set point. It remains at set point also 50%. Set point also 50%. Cross variable also 50%. That time, some disturbance is coming. Flow rate is decreased. Flow rate is because upstream pressure decreased. That's why flow rate is decreased. What will happen? The level will decrease. But controller will take necessary action and bring back the process again to 50%. This response is called regulatory response. Regulatory response. You have to do both these two. It takes only 15 minutes for each, half an hour. Remaining 2.5 hours, what you have to do? That first part. You have to obtain mathematical model. Manually, you bring the process to 50%. Then you have to give small change, record the value, get the reaction curve, get the mathematical model, tune the controller. Again, bring the process to 50%. You enter the tuning parameter. This and all will take 2.5 hours. After doing that, you can do servo response and regulatory response. Why you are doing servo response? If I change the set point, whether the controller works or not, I can check. If I change the set point, the controller changes the set point. Cross variable also changes to 55. I change the set point to 55. Cross variable also changes to 50. Regulatory response means any disturbance comes into the picture, whether the controller again makes it 50 or not. If no controller means any disturbance comes means any decrease in flow rate means it will come and settle like this. If any increase in flow rate, it will go and settle like this. No controller. If controller is there, it again bring back to same 50%. That is called regulatory response. If you the lab, usually I use demonstrate how to operate all these things. That is already available in the YouTube. So level process, if you select, that will be demonstrated there. That along with this knowledge, if you see that, you can understand. You can understand, or I will put that link